Welcome to this explainer. I am absolutely thrilled you're here today because we are going to look at one of the most foundational universe-measuring tools in all of mathematics. We are talking about exponents. If you took a completely standard piece of paper and folded it in half, just 42 times, its thickness would literally reach all the way to the moon. No joke. That staggering scale is purely thanks to the power of exponents. They are basically the ultimate mathematical shortcut for navigating extreme scales in physics, engineering, and, well, way beyond.
Okay, let's dive right into our roadmap for today. We've got 4 main stops. First, the anatomy of an exponent. Second, the core exponent rules. Third, special cases like zero, negative, and fractions. And finally, exponents in the real world.
All right, Section 1, Anatomy of an Exponent.
Formally speaking, an exponent is just a mathematical notation showing how many times a number is multiplied by itself. You've got your base a and your tiny raised n. It totally saves us from writing out endless, messy strings of multiplication. Instead, it gives us this beautifully clean, structured way to express rapid growth.
Think of your base number, like a 2, for instance, as an actor. The exponent, that tiny little 3 sitting up top, is the director. The director tells the actor exactly how many times to perform. So, the base 2 acts 3 times. 2 times 2 times 2. And 8 is our final result. You see, once you think of it as a relationship between a base and an instruction, the logic just clicks perfectly into place.
Moving right along to Section 2, the core exponent rules. Let's look at what happens when we multiply and divide powers that share the exact same base. When you multiply them, you simply add the exponents together. And when you divide them, well, you just subtract the bottom exponent from the top one. Multiplication pairs so elegantly with addition, and division pairs right up with subtraction. It's this incredibly beautiful mathematical symmetry that completely saves you from having to expand all those numbers out manually.
So what happens when our director gets a director? This brings us to our third core rule, raising a power to another power. If you have a base raised to a power m and that entire expression is raised to the power of n, you simply multiply the two exponents together. The base itself stays exactly the same, but your brand new exponent just becomes m times n. Easy, right?
Up next, Section 3, Zero, Negative, and Fractions. Time to look at some of the weird stuff.
I want you to just think about this for a second. The whole definition of an exponent is how many times you multiply a number by itself, right? But how do you multiply a number by itself 0 times? Or -3 times? It sounds like a total paradox, doesn't it? Let's see how mathematical laws step in to elegantly solve this.
First up, the zero exponent rule. Any base raised to the power of 0 is exactly 1, while as long as the base isn't 0 itself. I know, it feels a bit like magic, but it perfectly maintains the consistency of those core rules we just went over. Next, we have negative exponents. A negative exponent doesn't actually make your number negative. Instead, it creates a fraction. So a to the negative n simply becomes 1 over a to the positive n. And finally, fractional exponents. These actually represent roots. If you see an exponent of 1 over n, that is literally the nth root of your base. For example, 16 to the power of 1/2 is just the square root of 16, which gives us 4.
And that brings us to our final stop, Section 4, Exponents in the Real World.
Consider a massive number, like 3 times 10 to the 8th meters per second. That right there is the speed of light, roughly 300 million meters per second. Without exponents, scientists would have to write out endless, mind-numbing streams of zeros for their calculations. To put that into perspective, if you actually tried to write out the precise mass of the universe in kilograms without using scientific notation, you'd need a piece of paper over 100 feet long just to hold all the zeros. It's crazy. Exponents elegantly pack these massive, unwieldy concepts into tight, totally readable scientific notation. But honestly, it goes so much further than just keeping our math neat. Exponents are actively working behind the scenes in almost every major engineering and physics application out there. They're used to model signal attenuation, which is the math behind why your cell phone signal drops over distance. They calculate radioactive decay and nuclear physics. Down at the microscopic level, they plot out the exact curve of a battery discharging in your laptop, and they map out the enormous orbital motion of satellites. These simple little mathematical shortcuts literally bridge the invisibly tiny and the unimaginably massive.
Seriously, could you imagine mapping the trajectory of our moon or calculating the decay of an atom without these shortcuts? We'd be completely paralyzed by a sea of zeros before we even finished writing out our first equation.
So the next time you see that tiny little raised number, just remember, it's not just some dry math rule. It's the literal key to scaling the entire universe. Thanks so much for joining me on this explainer, and keep exploring.